And just so you guys know, we made $165 at the football game on Friday. That was pretty good. So we've made about almost $200 already this year. There's still a lot to go, but that's about 2 people, right, into Disneyland? Yeah, 1.5. But 1 3/4. It was only about 135 a person last year. That included the bus and the T-shirt. So. Okay, so what we're going to talk about today is a technique, okay? It can be a shortcut to integrating some complicated integrating problems. When we jump into, we're going to do chapter 7 again, which was all the volume and area stuff, okay? And then we're going to jump back into other integration techniques, okay, in chapter 8. This may or may not be on the AP test this way, okay? But it is something that AP has on their list of things that we're supposed to teach you, so that's why I'm doing it. All right. Again, it's a technique. It works for things that are set up in a very specific pattern. Okay, so if you see this, then you can use it. If you don't see it, there might be another way to integrate it. Okay, so right there, I think you have to fill some stuff in, right? I would write down both of those equations, okay, into that box there. Okay, so a first order linear differential is an equation that has this format, okay? It's got the derivative, okay? Typically we're going to see y prime, okay? Times a polynomial, or plus a polynomial times y equals another polynomial. And the 2 polynomials have to be continuous functions, okay? Typically they are, all right? So that's what a first order linear differential is. We're going to use something today called the integrating factor. You might want to write this in the left-hand column, okay? Integrating factor. And we're going to use the notation of I for our integrating factor. This is not in your book, okay? Which ends up equaling e to the integral of the p of x polynomial dx. So I'm going to do something the long way on the first example, and then we're going to take the shortcut on the other 3. Okay, so that way you can see where things will be plopped in. Okay? So I have to first of all look for the pattern. I start, do I have a derivative? Yes. Do I have a polynomial? In this case, the polynomial is just a 1. Okay, do I have a y equals another polynomial? Okay, so I know I've got a first order linear differential, so I'm going to use my integrating factor, okay? The p of x happens to be the 1, and the q of x happens to be the e this time. So the integrating factor is e times the integral of my p dx. Okay? Again, the integrating factor is something that I just taught you about, right? I said that's the formula we're going to use for integrating factors. E to the integral of the p, whatever the p function is, dx. So we're going to go ahead and integrate this, and it'll give us our integrating factor for this problem. So when I integrate 1 dx, what do I get? X. So my integrating factor, I don't use the plus c when I'm doing the integrating factor. The integrating factor is e to the x. Okay? So the other thing you might want to write as a note to yourself out in the left-hand column is that we multiply everything by the integrating factor. So multiply everything by the integrating factor. So I'm going to go back to my original equation, and I'm going to multiply both sides by e to the x. Equals e to the x times e to the x. So both sides got multiplied by my integrating factor. Again, I'm going to show you the long way right now. Okay, and then I'm going to show you where we can cut a whole bunch of stuff out. All right. So I would probably start this by distributing in the e to the x. So I've got e to the x, y prime, plus e to the x, y. I'm not going to write anything after it yet. I'm going to write an equal sign. Equals e to the 2x, right? When we add those up, we would get 2x. Now we're going to go ahead and integrate both sides. So I'm going to throw a dx after both of these things here. That's why I left the space. And I'm going to use some u substitutions. I need some. Okay? So my left side u substitution, okay, I am going to choose to use this piece right here, this e to the x, y. All right, it is a product rule. So when I take the derivative, I keep the first. What's the derivative of the second? What's the derivative of y with respect to x? dy dx, right? Or we can write dy dx as y prime. Okay? Plus, keep the second, which is y. Derivative of the first is e to the x with a dx after it. Do you notice? Okay, so I used the e to the xy as my u, but look at the du. Isn't this whole thing, this entire thing right here? So I'm not going to sub in the u, I'm only going to sub in the du. So I'm going to integrate du equals, let's finish the left side and then we'll go to the right side. Okay? When I integrate du, what do we get? U. And then I'm going to put my u back in, which is e to the x, y. I'm going to put my u back in, which was e to the x, y. So I just subbed for u, which was up here. Okay? All right, now we're going to do the right side. And typically in one problem, if we've already used a u substitution, we can't use it again. So I'm going to use a v substitution. Okay, so what are you going to use as your v, do you think, on this one? 2x, good. So dv is going to equal what? 2dx, and then I'm going to move the 2 over because I don't have that. So 1/2 dv. All right, we have e to the v, and what's going in for the dx? Okay, when we integrate e to the v, what do we get? E to the v, you guys got to be louder. E to the v plus what? What's wrong, Joaquin? Where did I get 2x? Right here. Right, I was using that u, or in this case a v instead of a u. All right, we good? Okay, so now I've got 1/2, and I've got 1/2 e. For the v, I'm subbing back in the 2x plus c. Okay. Now what I've got to do is I've got to get the y by itself, so I've got to divide everything by e to the x. I'm going to come over here and do that. Kind of put it right there. So I've got y equals 1/2 e to the 2x divided by e to the x plus c divided by e to the x. So I took this guy here and I divided it on both sides. I could clean it up a little bit. I could say 1/2. What do I do with the exponents when we have division? Subtract. So what do I really have? E to the 2x minus e to the x is e to the x. The only other thing I could do with this is bring it upstairs by making it negative if we wanted it all on one level for some reason. Okay, so now we're going to take, so this was our final answer that they wanted us to find there. They didn't give us something to plug in to find the particular solution, just general. So, the shortcut. You ready for the shortcut? Because we want to cross out a bunch of that work and not have to do it, right? This thing here could get really, really messy. Okay, so here's the shortcut. You're going to be able to get it right here to this spot right here. Okay? Whenever we have this pattern and we use the integrating factor, every time we integrate it, it's going to be the integrating factor times y. Do you see that? The integrating factor was e to the x times y. So when I go to integrate this piece here, it's always the integrating factor times y is the answer. Okay, so let's try that in the next one. We're going to use that shortcut. Okay? So, the first thing I have to set it up as is I have to make sure it's just y prime minus a polynomial times y equals a polynomial. I need to move that x. How do we move the x? Divide. So I'm going to divide everything by x to begin with. Okay? So I'm going to write it as y prime equals minus, let's try that again, minus 2 over x times y equals x, right? Because x squared divided by x would be x. All right, so this is my p function. That's my q function. I've got the y prime minus a polynomial times y equals a polynomial. So I've got the first order linear differential. Now I'm going to try to figure out my integrating factor so I can take the shortcut. Okay, so integrating factor is I equals e to the integral of p. What's my p in this case? Negative 2 over x. You're going to keep the sign with it, dx. Okay. When I take and I integrate it's basically 1 over x, isn't it? What do we end up with? Negative 2, what's 1 over x integrate to? Good. Natural log of x. And again, remember we just ignore the plus c part. All right, we're going to do some fancy algebra. I would like to be able to cancel the e and the natural log here in a second. Remember, we're allowed to take that and make it an exponent, but I'm not going to move the 2 yet. Okay? Or I'm not going to move the negative yet. So negative natural log of x squared. Is this exponent happy where he's at when it's negative like that? No, so we got to bring it downstairs. And then what happens with the e and the natural log? Cancel. What's wrong?
Why'd you move the 2 to the back? I mean, yeah.
Why? Because I can't cancel the e and the natural log till everything's off the natural log in the front of it.
So you can do that, right?
Yeah, because this is one of the properties we learned in Algebra 2.
Alright.
Okay? And one of our log properties is we can take that and make it an exponent. Okay? Alright, so my integrating factor is 1 over x squared. Alright, so here's we're going to start to use this method. We go back to the original. I'm going to go back to this line of the original, though, where we had the pattern set up, right? And I'm going to multiply everything by the integrating factor. So 1 over x squared times y prime minus 2 over xy equals 1 over x squared times x, and then we integrate both sides. So that's where my integral symbol comes from. Dx, dx. Alright, so what I just told you in the last problem was the shortcut on the left side is all I have to do is I have the pattern set up right is I take the integrating factor times y. That's what this will always, always integrate to. So I'm done integrating that. If you know the pattern, that was nice, wasn't it? We skipped like 400 lines of work. Okay, probably not quite that many, but close. What is this going to simplify to over here on the right side? 1 over what? 1 over x, right? Because this is going to cancel and that's going to go down to an x. Dx. All right, when I integrate over here, what is 1 over x integrate to? natural log of x plus what? C, good. I have to get y by itself. How do I move the x squared? Multiply. I'd be okay with you leaving it like that. That was much better than the first one, right? Even though it was probably uglier, it was much better because I got to take this shortcut. So again, the shortcut is when you have the integrating factor times the function, it's the integrating factor times y when it integrates. Okay? All right, let's try example 3. Nobody's there?
No.
Sometimes the class across plays with the ball and they hit the window once in a while, but okay. They just wanted to make sure we were awake. All right, so let's check it out and make sure we have the first order linear differential. So first I have to have a derivative. Do I have the derivative? Do I have a polynomial function? Do I have y? Do I have another polynomial function? Yes, and luckily these have stayed pretty simple. The homework might not be as nice, but hopefully you'll get the idea here. Okay, so let's set up our integrating factor. So our integrating factor is e to the integral of, what's my p function? Negative 2x dx. Okay, so I've got to integrate that. So I know it's going to be e. When we integrate, we would get negative x to the what power? Squared. When we divide by 2, what happens with the 2 and the 2 in the denominator? It goes away. So I just get e to the negative x squared. Is everybody okay with the step I skipped? Yes? No? Okay, so let me do the step. So we would have 2, and then we would divide by our new exponent, right? So these guys would cancel, e to the negative x squared. Okay? So that's my integrating factor. The next step, and I'm going to do the next step over here, is that we have to take and multiply the integrating factor by both sides of the original function. So we have e to the negative x squared times y prime minus 2xy equals e to the negative x squared times x. Then we are supposed to integrate both sides, so I have to throw the integral symbols and the dx's on there. Okay, let's use our shortcut. So when I see this, what do I get when I integrate it? Times y. Perfect. That's it, right? You just have to remember that that happens. Okay? To integrate this side over here, what am I going to need? U substitution. Good. So what's your u going to be? Negative x squared. Excellent. So du is going to be what? Negative 2x dx. So what am I missing? The negative 2. Good. So I'm going to move the negative 2 over as a 1/2, and we're going to go ahead and sub in. So I get e to the u for the x dx. What are we putting in? Careful. Negative 1/2 du. Good. All right, so the left side stays the way it is. The right side, when I integrate e to the u, what do we get? E to the u plus c. Instead of writing u, though, what should I write down for u? Gentlemen, I hope we're paying attention. Because if we're going to talk, I'll just give you a pop quiz on it now. Okay. All right, because it will be on the test, so you want to make sure you're learning this right now. All right, in order to get rid of this thing right here, what do I need to do? Divide. So I'm going to show that divide step at least on the left side here, because it's kind of ugly. So what happens with these two here? They cancel, so I've got negative 1/2. Is this guy happy where he's at? No, so bring him upstairs because he's a negative exponent. That's it. But look at how that could have gotten really ugly with all of that on the left side, and we're able to take that shortcut because it fit this pattern. Okay? Everybody good? Kaylee, did you have a question? Did you figure it out? I figured it out. Okay, good. All right, let's go one more. So we hadn't done any trig yet. Let's do one with a trig. Okay? So we have to check and make sure we've got the right pattern. Do I have a derivative? Do I have a function times y? It's not in the same order, but we do have a function times y. They wrote it like that because of the trig on the tangent. We didn't use parentheses on it. Equals another polynomial function. Does that work? One's a polynomial function. It's just one, right? The horizontal line. Okay. So integrating factor. E to the integral. What am I going to put inside the integral this time? Tangent t. And technically it's not just tangent t, but negative tangent t. Does everybody see where the negative came from? Yeah, see that negative sign right there? dt. Okay. In your textbook, a integral you probably haven't memorized yet is the tangent integral. Okay, the tangent integral, there's a negative there, is negative natural log of the absolute value of cosine of t. So if you get to run into one like this on the homework, you go to that inside front cover of your book and you look up the integral if you don't know it. Okay? Again, there was a negative here, and then there was a negative when we integrated that tangent. It integrates to a negative. What's going to happen with that double negative? Positive. What's going to happen with the e and the natural log? They're going to cancel. And this is going to stay positive, so we're going to drop the absolute values on it. Okay? All right, let's go to our pattern now. Okay, so I've got to take the integrating factor and multiply it by the original. So cosine of t times y prime minus y tangent of t equals cosine of t times 1. All right, what do I have to do to both sides now? Integrate, which so I'm going to put the integral symbols in there. I'm going to throw some dt's after it. This one's actually really nice. Okay, so the left side we know integrates to what? Cosine t times what? Y. Perfect. When we integrate cosine, what do we get? I like sine. Should be positive or negative? Positive. Integration, it's positive. Derivative, it's negative, right? And then I have to put what in? Plus c. Because we're integrating, not taking the derivative. Okay? All right, now I have to get this thing off the y, right? How do I do that? Divide it. So we end up with sine of t over cosine of t plus c over cosine of t. It is tangent. Very good. What's this one?
Just c, right?
No. 1 over cosine, which is equal to what? Secant of t. It's probably we would probably write c secant of t. Put the coefficient in front. Okay. All right, that is it. We finished pretty quickly. Okay, very little whining. Huh? Okay, well, you got to practice it, right? Once you practice a few of them, you're going to get the pattern down. Okay? Yes, Anna. This, it's a memorized integral. It's in here front of your book, right? So if I went to here and I went and I looked up my integral of tangent, it would be that, okay? And it's not one that I would have had to look it up too, okay? It's not, I mean, you're supposed to have that one memorized, but it's not one of the ones we use a lot, so I would be looking it up, okay? All right, so you're on haiku right now. So everybody get to haiku. And you've got some time, so you're going to